Hello, everyone. My name is Morenzo, and here are my groupmates Akshita and Savan. And for our CSCE 440 final project, we're doing an air quality analysis in Delhi, India. So, introduction. So, air pollution is a significant environment challenge, especially PM 2.5, which are air particles that are smaller than 2.5 micrometers. They're a critical pollutant linked to health risks. We're using regression analysis to model the relationship between PM 2.5 and carbon monoxide levels. We do this by leveraging exponential and polynomial regression techniques. We're doing it in linear, quadratic, and cubic. PM 2.5 levels can be modeled and analyzed with numerical methods. And lastly, we're doing Simpson's method to compute cumulative exposure to pollutants over time, focusing on those that are strongly correlated with PM 2.5. So this is the problem statement. Air pollution poses a significant threat to public health with particulate matter less than 2.5 micrometers in size. We're referring to it as PM 2.5, being a critical pollutant linked to severe health issues such as respiratory and cardiovascular diseases. Effective air quality management requires understanding of the factors affecting PM 2.5 levels and developing the predictive tools to aid in the decision-making process. So these are the challenges that we faced. Identifying which pollutants have the strongest influence on the PM 2.5 levels. And then next, we model the relationships between PM 2.5 and the other pollutants for better predictions on its behavior and also to meet the World Health Organization standards, which is PM 2.5 levels less than 15 micrograms per meter cubic and quantifying cumulative exposure to pollutants over time to assess long-term health risks. And finally, evaluate the effectiveness of numerical algorithms in practical environmental applications.
So to go over the data set that we used for this was data collected from Delhi, India, and this was collected in between November 2020 to Jan 2023, so approximately 2 years of data. The data consists of particulate matter, PM 2.5 and PM 10 levels, carbon monoxide, nitrogen dioxide, sulfur dioxide, ozone, and ammonia. We converted this hourly air quality data to a bi-weekly averages to reduce the size of the data to make sure the algorithms works best. Our initial consideration was to compare PM 2.5 levels across time, but this violates the core principle of regression, that is that is the independent variables are independent of each other, and also there. For example, cubic polynomial has at most two turning points and then it diverges. So there are also limited turning points. So we decided to switch to PM 2.5 versus other pollutants. This included all the pollutants and compare them in different regression algorithms. We first started with the exponential regression algorithm. This captures the nonlinear growth or decay patterns. Um, we applied to we applied the min max scalar to normalize the pollutants to a range of 0 to 1 and also added a small constant to PM 2.5 to handle the logarithmic transformations and extremely large values. Our two main metrics to measure the performance of the algorithm was R square score, which measures the fit accuracy, and the mean square error that quantifies the prediction error. So to go over through the results, the first graph here is PM 2.5 versus carbon monoxide, and the red line shows the best fit line. We computed best fit line for all of the pollutants versus PM 2.5, and we also predicted values of PM 2.5 levels for future carbon monoxide concentrations. In this case, for um, 4195.83 micrograms per cubic meter carbon monoxide will predict the value of 338.09 micrograms per cubic meter. So these are the different graphs for versus other pollutants. As we can see, NO and NO2 also performs comparatively well, but O3, NH3, and SO2 does not perform well in exponential algorithm. So for the final analysis, carbon monoxide performs the best and shows the highest relation with highest R square score of say, 1637 and lowest mean square error of 0.9. The advantages of this algorithm is that it's suitable for modeling exponential growth or decay trends, but the main limitation is it cannot capture nonlinear monotonic relationships. And for the computational complexity of this algorithm is it fitting requires iterative optimization but remains efficient for small data sets. So we decided next to perform polynomial regression as it tackles the limitation of this particular algorithm.
Okay, so we decided to use polynomial regression, and the models that we used were linear regression, which means fitting a straight line through the data points. Also, quadratic regression, which includes a squared term to capture some curvature. And finally, we also did a cubic regression where we included a cubic term to capture the more complex patterns. And the metrics that we used to measure were R square scored, which measures the model accuracy by proportion of the variation. And then we did prediction by utilizing the model to estimate CO levels required to achieve the safe PM 2.5 threshold set by the World Health Organization. And the software we used was implemented in Python using the normal equation. So here are the results. It showed some similar performance in terms of R square, with all of them just differing starting from the third decimal point. But overall, they performed pretty similar. And they also predicted CO levels to achieve the PM 2.5 threshold of 15 micrograms per cubic meter. And the linear predicted that it's 657.53. Quadratic predicted 655.69 and cubic predicted negative 350, which is not possible as a volume because having negative volume is not possible. So it's invalid for predicting CO levels to reach the threshold for the cubic regression. So analysis. Linear regression is simple, efficient, it has interpretable results, and an accurate prediction. Quadratic regression has more flexibility with the quadratic term, but the added complexity had no significant impact on the R square score. And finally, cubic regression. It risked overfitting and unrealistic predictions, which was the negative CO levels, which is not suitable for this data set. And the computational complexity, linear regression is the simplest to compute. It's a 2 by 2 system, while quadratic and cubic regression involves larger matrices and it's definitely going to take longer to compute.
So the last method that we have is the Simpson's method. Our purpose to use this method was to calculate cumulative pollutant exposure over time, which focused mainly on pollutants which had a strong correlation to PM 2.5. So we selected the top three pollutants, which was NO, NO2, and SO2. As you can see, NH3 was also amongst the high pollutants, but we did not use it because its standard deviation was pretty low. And we also did not use carbon monoxide because of its overwhelming dominance. As you can see here, we have the cumulative exposure graphs of all the three pollutants, and we can see that it was calculated over equal time intervals, which was 6 of the years or 2 months, and the exposure levels aligned with the correlation to PM 2.5. As you can see through the cumulative trends of pollutants over the time, that the highest cumulative exposure was for NO2, followed by SO2 and NO. The cumulative exposure for NO2 for the 4 years was for 2020 was 426.52 micrograms per meter cube. For 2021, it was 342.10 micrograms per meter cube. For 2022, it was 318.70 microgram per meter cube, and for 2023, it was 346.42 microgram per meter cube. So for analysis, we got the insights that SO2 and NO had higher cumulative exposures but showed consistent trends. Effectively, they effectively quantify cumulative exposures and capture the pollutant trends over time. Um, and the advantages for using this method was it handles irregular data by dividing it into equal intervals. So it really helped when we had missing data points. And but the only limitation is that it requires evenly spaced data points. So for our conclusion for our methods is that high R square for both exponential and polynomial regression suggests that carbon monoxide levels can be a reliable predictor for PM 2.5 levels in the region. Exponential regression captured nonlinear relationships between PM 2.5 and other pollutants, but it assumes a monotonic relationship. Linear regression is the most suitable for this data set. So if our boss were to ask which method was the best, then it would be linear regression because it was interpretable and had accurate results. It avoided the issue of overfitting and unrealistic outputs, and it was computationally efficient and easy to implement. Simpson's method was a little different, but it quantified the cumulative pollutant exposure for the three pollutants over time. Here are our reference, and thank you.